Ever wondered how the universe whipped up elements in just a few minutes after the Big Bang? The universe is about 10 seconds old. It's a hot, dense soup of particles. Quarks, electrons, and neutrinos are zipping around. But it's all chaos. Then, as the universe cools down, quarks begin to stick together to form protons and neutrons. Now, fast forward to about 3 minutes after the Big Bang. The temperature drops to a few billion degrees. Protons and neutrons start to fuse. This process is what we call Big Bang nucleosynthesis. It's the universe's very first chemistry set. About 25% of the universe's mass becomes helium-4. And it doesn't stop there. We also get small amounts of deuterium, which is a proton and a neutron, and helium-3, which has 2 protons and 1 neutron. Oh, and don't forget lithium-7 with 3 protons and 4 neutrons. But not all of these elements are stable. Let's zoom in on helium-4. Once temperatures dropped, about 25% of the total mass in the universe became helium-4. Out of every 16 nucleons, 4 combined into one helium-4 nucleus. You see, there's far more helium-4 in the universe than can be explained by stellar nucleosynthesis alone. If the observed helium-4 abundance had been significantly different from 25%, it would have posed a serious challenge to the Big Bang theory. In the mid-1990s, some observations even suggested a potential crisis, but further studies confirmed that the universe's helium-4 levels matched our predictions. Let's shift our focus to another crucial element, which is deuterium. Unlike helium-4, which is very stable and difficult to destroy, deuterium is only marginally stable and easy to destroy. Interestingly, there are no known post-Big Bang processes that can produce significant amounts of deuterium. This makes deuterium a unique probe into the universe's origins. Observations of deuterium abundance suggest that the universe is not infinitely old, aligning with the Big Bang theory. During the 1970s, scientists made significant efforts to find processes that could produce deuterium, but these attempts only revealed ways to produce other isotopes. The abundance of deuterium observed today fits well with the Big Bang model, but is too high to be consistent with a universe composed mostly of protons and neutrons. Talking about Deuterium Bottleneck. When the universe had cooled sufficiently to allow deuterium nuclei to survive disruption by high-energy photons. It's important to note that the Neutron-Proton freeze-out time occurred earlier during the phase when the universe was highly radiation-dominated, which controlled the temperature and time relation, making the process almost independent of dark matter content. At this critical juncture, there were about 6 protons for every neutron. However, some neutrons decayed before they could fuse in the next few hundred seconds. By the end of nucleosynthesis, there were about 7 protons for every neutron, and almost all the neutrons had combined to form helium-4 nuclei. Free neutrons being less stable than helium nuclei, consequently any deuterium formed was immediately destroyed, a situation known as the Deuterium Bottleneck. This bottleneck delayed the formation of helium-4 until the universe cooled enough for deuterium to survive. Once the universe reached this critical temperature, there was a sudden burst of element formation. However, very shortly thereafter, around 20 minutes after the Big Bang, the temperature and density dropped too low for any significant fusion to occur. At this point, the elemental abundances were nearly fixed, with only minor changes resulting from the radioactive decay of tritium and beryllium-7, the 2 major unstable products of Big Bang nucleosynthesis. Let's move on to another aspect, the cosmological lithium problem. The abundances of all light elements depend on the amount of ordinary matter, or baryons, relative to radiation or photons. Since the universe is presumed to be homogeneous, it has one unique value of the Baryon-to-Photon ratio. This ratio was crucial in testing whether all light element observations could be explained with a single value. Precision observations of the cosmic microwave background radiation with the Wilkinson microwave anisotropy probe and Planck have provided an independent value for this baryon-to-photon ratio. However, there's a significant discrepancy when it comes to lithium-7. The observed abundance of lithium-7 in population 2 stars is a factor of 2.4 to 4.3 lower than the theoretically predicted value. This discrepancy, known as the cosmological lithium problem, poses a challenge for the original models. Let's delve into some non-standard scenarios in Big Bang nucleosynthesis. These scenarios assume that the Big Bang occurred, but introduce additional physics to see how this affects elemental abundances. Non-standard BBN should not be confused with non-standard cosmology. While standard BBN relies on a homogeneous universe and known particles, Non-standard BBN relaxes these assumptions. It may introduce new particles, such as massive neutrinos, to test their impact on elemental formation. Historically, one reason for researching non-standard BBN was to resolve inconsistencies between BBN predictions and observations. However, better observational data often resolved these inconsistencies, and modifying BBN usually led to more discrepancies rather than fewer. In the early 21st century, the focus of non-standard BBN research shifted. Scientists began using BBN to place limits on unknown or speculative physics. For example, by introducing a hypothetical particle like a massive neutrino, researchers can determine the conditions under which BBN predicts abundances that diverge from what we observe. In conclusion, the Big Bang nucleosynthesis provides a fascinating glimpse into the early moments of our universe. From the formation of the first nuclei to the intricate dance of particles, this cosmic recipe has shaped the very fabric of our existence. The story of Big Bang nucleosynthesis doesn't end here. Future advancements in technology and observational techniques will undoubtedly shed more light on the mysteries of the early universe. New telescopes and particle accelerators will allow us to peer further back in time and understand the conditions that led to the formation of the first atoms. Moreover, the ongoing research into non-standard BBN scenarios will help us test the limits of our current theories and possibly reveal new physics that could change our understanding of the universe. Each revelation brings us closer to answering the fundamental questions about our origins and the nature of reality.